Continue with what we started in the last lecture. So, let's see. So, in the last lecture, what we did is a bit of analysis of energy eigenstates, etc., using random matrix theory. And just to refresh your memory, what we found is that the matrix element of any operator in this, in this set of eigenstates which follow this random matrix theory is just given by O del delta Mn plus some number, whatever that is, some number divided by d, where d is the Hilbert space dimension, times what was it, times some random number, okay, which has a mean 0 and variance 1. That's the first result that we had. The second result was that we looked into these energy eigenstates, and we found that when you have an integrable model, okay, then the average level spacing ratio, which we defined in the last class, was went at 0.38, okay, and we derived an analytical formula for this, okay. So we stopped there, and then we said that we are going to do an analogous thing for the ergodic systems, which followed either a GUE or a GOE, okay. Now, what I'm going to do here is to just show you how to do this, rather than doing the integrals explicitly, because those are complicated, and it's best that you guys work this out at some point if you have time. But the main point about doing this thing is to realize that when a system is ergodic, when it's not integrable, energy is not uncorrelated random numbers. And we found that the gap distribution, the distribution of energy gap, went at some a omega to the power beta by times this, okay. Now, therefore, this gap, if you have two energy levels, E2 and E1, this gap essentially tells you that this factor is E2 minus E1 whole to the power beta, okay. This is for a two-level system. But the question is, we really didn't get into how this gap distribution, or in other words, energy distribution would look like if I went to, larger system sizes, okay. So in this case, there is a conjecture. It's typically called a Wignall-like surmise in the literature, and which says that for a collection of this energy eigenstate, P of EI, okay, would go as product over J less than I, EI minus EJ whole to the power beta, okay. So it just tells you that the correlation is built in just to protect the level fluctuation, level repulsion, so that there is no zero energy gaps out here, okay. And then you just put in this factor to ensure that at large enough energy, this probability would have a very little weight. It will just decay. This is just so this essentially is just a guess, but it turns out that if you take this and you do numerics, you get quite a good result, and this is easy to understand, because what you are doing is you are building in this correlation, of this level repulsion, and you are also building in this thing that at large omega, this thing is going to go as omega square. It's a decay. So these two facts are built in, and therefore, this gives a good result. And of course, there is a normalization, which I ignored. Okay, so that's there. Now, the point is that if you have n such levels, it's very hard to do anything analytically using this. So what some people did to calculate, levels ratio, so this ratio of level that statistics is to just take 3 levels so that they can have these 2 meaningful levels. So let me just call these as so 3 levels, E1, E2 and E3, okay. And therefore I'm going to take this E2 and then define an R which is E3 minus E2 by E2 minus E1. Okay? Because if I have these 3 levels, then I have my delta n and delta n minus 1, which I defined in the last class. Okay? And the ratio between them is the ratio of adjacent gaps. Okay? Is that clear, or is there something? So
E3 minus E2 is lesser than.
No, I'm going to take that to be the lesser. That's my choice. Okay. If it's not the case, I'm just going to switch 3 and 1. Okay. That doesn't change anything.
These levels are one after the other.
Yeah. So this is 1, 2, 3. Okay. So and the adjacent levels are there for E3 minus E2 and E2 minus E1. So the minimum and the maximum is arbitrarily chosen, but I'm going to take this choice. Right? So now to have the probability distribution of R, what do I need to do? I need to find out this. So what I need to find out is the following. So P of R would be some normalization, and then I have to integrate over dE1 up to dE3. Okay. P E1 E2 E3, which was something that can be written from there. Okay. Notice that this now is not of a product form, saying that unlike the integrable models, this is not uncorrelated energy levels. And then delta of R minus E3 minus E2 by E2 minus E1. This one? Well, this is sort of so I needed to encode 2 things. One of them is that there should be no level crossing, because you need a level repulsion. Okay? So that's that factor. So every 2 levels should be such that when they come right next to each other, this probability would vanish. And the other one is to say that if you had a particularly large energy, the weight would be small. That's the Gaussian decay. Okay.
It's just from the P omega.
This is just taking Q from the 2 levels and then trying to generalize it, keeping 2 distinct features.
But EI minus EJ whole square only gives some other terms.
EI minus EJ whole square? Oh, here. Yeah, but you can, if you wanted to write it in gaps, you can write quadratic forms in gaps as well. There would be some. See, the point is what would happen. I mean, there would be some E1 square and then some E1, E2 and then all those things. But I can make a transformation and then just, talk in terms of those E primes. Okay, and just write it like that. I mean, these two do not give different properties at large omega, in particularly.
And this is the probability distribution in which the energy values are like, they go from they are like arranged in ascending order, or?
Yeah, they are arranged. See, there is this I greater than J. Yeah, so yeah, they have to be. Otherwise, you are going to miss count twice or do stuff like that. So that is something that you. Yeah.
What is this lambda bar?
Lambda bar. Product. That's the sign of a product. Sorry. Okay. It's a product over. So if you write it down, it will be E1 minus E2, then E2 minus E3, then E3 minus E4, and so on. It's a product of all those. Okay. Or rather the other way around, actually, because I is greater than J. So it's like, so if you write this down, it is En minus 1 times En minus 1 minus En minus 2, and so on. That's the product. Okay.
Sorry,
yeah.
I still have a doubt regarding the exponential.
Mm-hmm.
So what we wanted to ensure was that a large gap is suppressible.
Yes.
But like, again, I'm still unable to understand. When we are just writing EJ, that just means any large energy is suppressed. How is that?
Yeah. So no, these two. So all I am saying is that the point is that since they are level spacings, if you think of these level spacings and think of things in the middle of the spectrum, okay, then you would see that if you start from a given energy, these are really tiny level spacings and they go on. So with respect to that, if you put a large energy out here, it's exactly same as putting a large gap. So I'm not saying this will be numerically exactly the same. I'm saying that the qualitative feature is going to be the same. And in principle, you can put a gap there. I mean, but that will make it more correlated and difficult to work with. That's the idea. Okay. Fine. So out here, what we then do is to define two variables. Okay. One is x, which is E3 minus E2, and the other one is y, which is E2 minus E1. And the third variable is just E2. Okay, so we are going to switch to these variables. And the reason for this is clear because this is now becomes a function of y and x, and E2 would be eliminated from this delta function. So, by the way, I should probably say that in the literature when they write this thing, this beta, this exponent, which is 1 for GOE and 2 for GOE, it has a name, it's called Dyson index. Okay, because it's after the name of Dyson, who essentially did this. So, Gaussian orthogonal ensemble, where the matrix elements were real, and Gaussian unitary ensemble, where they could be complex. Okay, still maintaining Hermitian structure. Okay, so then in this case, what one can do, and this is the first exercise, after you write this in this form, you see that the product that appears here will be something like E3 minus E2, E2 minus E1, and so on and so forth. That you can write as x to the power beta, y to the power beta, and then there is a x plus y to the power beta. And that's the E3 minus E1 part. Okay. And then there is this delta function, delta x by y. Okay. Now, once you do this, the only remaining dependence of E2 is in that exponential. Okay. So the task is to write down this this exponential in terms of x, y, or any linear combination of x, y, square of them, and some piece which only has E2. Okay. If you do that, and this is the second homework, you can show that this summation Ej square by 2, j equal to 1 to 3, can be written as half of x square plus y square minus 1/3 x minus y whole square plus a piece which depends only on E2. Okay, it's a quadratic piece out here. So this piece is just some number times E2 square. Okay. This is another algebra that one needs to do. Okay. But the point is that then the E2 integral becomes trivial. Okay, it just can be done and you just can see this as some contribution to your normalization, which I don't care about. And therefore, this thing is just this integral, therefore. Sorry? Yeah, there is a, there is a dE2 here, that's correct. But the point is that integral will be trivial and I will do that. So, after I do all this, this P of R would be integral dx dy exponential of minus half x square plus y square minus 1/3 x minus y whole square x to the power beta, y to the power beta, x plus y whole to the power beta, and then a delta function of R by x minus y. That's the double integral that one needs to do. So amazingly, this can be done. Okay, and okay, you can give it in Mathematica, it can do it. You can think about it a little bit how to do it, and then think of this. But it's a lengthy procedure, so I'm not going to do this. So after taking all normalization into account, this P of R turns out to be R plus R squared to the power beta by 1 plus R squared to the power 1 plus 3 beta by 2. Okay, that's the result for getting the distribution of this, and it's quite a bit of work. Okay, I'm not saying that this is very easy and it will be very trivial to do, but the point is that this at least gives you an analytic expression for this P of R. Okay.
That's 1 plus 3 beta divided by...
Sorry, 2. Sorry, probably this, yeah. 1 plus 3 beta divided by 2. Okay. So, and then what one needs to do, the last step is average R, which is, this is normalized. So, this is R, P of R, dr. That's the average value. Okay. And again, this is an integral that one needs to do. And if you do this, you are going to get an analytical answer, which I'm going to write down actually. So the answer turns out that if beta is equal to 1, sorry? 0 to 1, sorry. Yeah. If beta is equal to 1, which is the simplest case for GOE, this integral just gives you 4 root 3 minus 2. Okay. That's the analytical answer. And if it is 2, then it gives you 2 root 3 by pi minus half. Okay. So if you take this is very close to some 0.54. Sorry? Okay, I should probably write. This is for beta equal to 1. This is for beta equal to 2. Okay. So the point is that this quantity is very close to the numerical value when you actually get this from some exact n-level numerics. So this quantity is close to 0.54, I think, and this is close to 0.6, which are the values of average level statistics for the Gaussian orthogonal and the Gaussian unitary ensembles. Okay. So the point is that one can sort of do this and understand in a reasonably simple way, I shouldn't say simple, in an analytic way as to why these level statistics essentially show up. And it's an amazing fact that once you put in the right characters in some sense, in the sense that there should be this level repulsion and the gaps should vanish and etc. This simple 3-level problem gives you a result which is almost numerically exact. Okay. So if you do this in a very large computer and you do your level statistics, the answers that you get is remarkably close to this. So what it shows is that it's really these properties of level repulsion and the Gaussian decay of the gap, which is really important for getting these average things. The details of the system doesn't matter that much. Okay, and that's why it's universal. Yeah.
Yes, so the avoided crossing happens only because we have a correlated system. It does not happen in the uncorrelated system.
Yeah, so an uncorrelated system in that sense is what I would call an integrable system. And there the energy levels themselves are uncorrelated random numbers in some sense.
So the ergodicity only happens
Yeah, the ergodicity only happens in this kind of correlated systems, where the system is ergodic, where there is no conserved charges, apart from the global symmetries, of course. And another thing which I probably didn't make clear in the last class is that all of this is after you have resolved all the global symmetries and gone to one symmetry sector of the theory. Okay. So that is an important point because if you take two symmetry sectors and do statistics between them, you may see level repulsion. Level crossing. There is nothing to prevent it because they don't talk to each other. They are completely uncorrelated. But that's not the sense in which random matrix theory works. It's only after you have resolved all global symmetries. Okay?
So is there a reason to think that I should only consider the Gaussian behavior of the tail?
Only consider meaning what?
Yeah, I mean, we're basically we're writing down the trace, right? Trace square.
Yeah.
But I can take also other power on that.
No. See, the point is that, so we exactly worked out the two-level problem, right?
Yes.
So we know how the gap scales.
Yes.
So take the Q from that. The power is omega to the power beta times this Gaussian. That's where the Q comes from. So if you write something and then you reduce it to two levels, you should be able to reproduce at least qualitatively that, and that's where the Q comes from. Okay. Yeah.
Can you please say what is the ergodicity that you keep saying in context of this system?
Well, ergodicity means it's not an integrable model. Your system can explore the entire phase space in some sense. Okay. So
How does exploring the entire phase space?
well, just why don't you hold on? I'm going to discuss this random metric, this adjusted thermalization and that kind of thing. There we'll see what it means. Okay. Yeah.
I had some questions on singularity.
Yeah. What was the?
I was going to ask about the fact that you said something about symmetries.
The symmetries. What I mean is that the global symmetries. See, when you write your Hamiltonian as a matrix in any computational basis, there are this symmetry sector which creates the blocks. All I am saying is that you do that analysis within a given block after resolving the global symmetries. That's all I mean. Okay. Yeah.
So we can use this level ratio statistics without unfolding it, without making a mean density one. But is there any physical reason why this works even without unfolding?
So there is a calculation. I don't have this at the top of my head, but people have shown that for this particular thing, the information of the density of state is not important. And that's why what mean density you put in and the information about density of state doesn't come in. Actually, this is precisely why you do this, because in a complicated enough system, having this density of state is an overall burden. It's not that easy. So this unfolding is not necessary out here. So these people have shown, I don't have it at the top of my head. I can point you to some references and yeah. Okay, if there are no further questions, this is what I intended to cover in lecture 1. Okay, so this is done now. But I'm going to start now with this eigenstate thermalization hypothesis and how it improves upon random matrix theory. But before that, let me give you the references for both this random matrix and the ETH part. And the standard reference is this review article by Regal, Polkovnikov, I think D. Alessio, and Kafui. And this is Advance in Physics in 2016. Okay. So that's the main reference from which this is taken. And the second one is that there is a PRL. Okay, let me. So there is a PRL by these guys. This is PRL 110 084101 2013, where this calculation of this random matrix, how to get this level statistic ratio is given. So essentially, these are the two things from where I have taken most of the elements, and then there are other literature, but this is what it is. So now let me okay. So let me start with this thing called eigenstate thermalization hypothesis. So to understand why we need this and what kind of thing this quantity is, first let's come back to basic quantum mechanics. Okay, and we want to see that suppose we have a wave function psi, okay, and it evolves by some quantum Hamiltonian so that I get some psi of t. Then I want to find out what's the expectation value of a generic operator in psi of t. That is the expectation value of this operator after some time has elapsed. So you see, the simplest way to do this, which we learned in our quantum mechanics class, is to write this psi of t in the eigenbasis of the Hamiltonian, assuming that we know it somehow. So these CMs are the overlap coefficient of psi at t equal to 0 with the eigenbasis. Okay, so CM is, this is psi 0 m. Maybe this is CM star, right? Yeah, whatever. So it's just the overlap, and these are the energy eigenvalues. Okay. Knowing this, it's simple to take expectation value of O, any operator O, and this would be, of course, summation over m and n, Cm star Cn e to the power I epsilon m minus n, and then OMN, where OMN is the matrix element of O between the states, eigenstates m and n. Okay, and this expectation meant psi of t, O psi of t. This is a time dependent object. Now in this I can separate out the terms where Em is equal to En and where it is not. Okay, so that, assuming that there is no degeneracy, and this we can do because we already saw that in a ergodic system we don't have this level repulsion. So I can write that Em equal to En also means m equal to n. Okay, and therefore this is mod Cm square OMM plus m not equal to n, Cm star Cn e to the power I epsilon m minus epsilon m t by h bar OMN. Okay, that's it. So you have a piece which is independent of time, and that's apparently your steady state value, and you have another piece which is dependent on time. Okay, so now the logic to how the system attains a steady state is by saying that at long enough times, you know, this epsilon m minus, so when t is much larger than this energy, inverse of these energy gaps, this is going to be a rapidly oscillating function and it's going to die down if I take a average over some time period. And then this would be left with this. Okay? Now, so the quantum mechanical answer for what would be the steady state value is this quantity, and it would reach that steady state at a time which is roughly greater than the inverse of this gap. Okay, so these two are the things that quantum mechanics tells you. Now, what does statistical mechanics tell you? Statistical mechanics tells you, oh, you have a generic system. Okay, I want to calculate the expectation value. I know that's just the average with respect to the microcanonical ensemble. Okay, so StatMech would tell you that O average at long times is trace of rho me times O. Okay. Whatever that rho me is. You construct your microcanonical ensemble, take your expectation, and that's that. The question is, are these two equal? Okay, and you immediately see they cannot be equal, because when you do this in a standard statistical mechanical system, you have completely thrown away all information about the initial state dependence. Okay, because this is typical, you know, there are many names to this. You can say that the system has explored the phase space. You can also say, and nowadays people are calling it scrambling in some sense, that you put in some information in a given state. If the system is ergodic, you let it evolve for some time, and then there is no local measurement which is going to allow you to retrieve that information. Okay, this phenomenon is typically called scrambling. It's very popular in the context of this out-of-time correlators and all that. But bottom line, all the memory of the initial state is erased. Okay? So the system doesn't retain this memory. Here, however, you see that if I don't assign a structure to this OMM, it clearly depends on Cm square. And Cm square retains the memory of the initial state through this overlay. So that's the first problem. The steady state prediction from StatMech and QuantumMech are different, okay, unless you put in something more. The second thing is that you can ask that when does this system reach the steady state? And there also there is a problem. Because these M and N are energy states which explores the entire Hilbert space in principle. And therefore, so if you have a system with let's say a finite Hilbert space, towards the middle of that Hilbert space where there are these thermal states, this gap essentially is order exponential minus L. They get more and more packed as you go towards the middle of this Hilbert space. So delta epsilon is order exponential minus L. Okay. This means that your time has to be order exponential L at least before you can ignore these terms and reach a steady state. Okay. Now, you can try to compute this for yeah.
Why the time should be?
Oh, because the time has to be larger than the inverse of the energy gap. So if the energy gap goes as exponential minus L, the time should be at least order exponential L, right?
Okay, the maximum.
Yeah, the maximum, yeah, sure. Because otherwise, the fluctuations from those states are going to matter. You are not going to reach the steady state, right? But typically in a laboratory, you don't see that. In a laboratory, what you see is the StatMech answer, and StatMech also tells you that this thermalization is, for our ergodic system, is generally fast. Okay? So how do we resolve this apparent paradox between the prediction of quantum mechanics and the prediction of StatMech? That's where this eigenstate thermalization hypothesis comes in. And this hypothesis is how you understand how to weight your quantum mech results and make them consistent with StatMech. Okay? So that's sort of why we need the ETH. Now, before I go to this ETH, let me just point out that suppose I now say that this system that you are talking about just obeys my random matrix theory. Would that work? Well, apparently what happens is this becomes a O bar, which is completely independent of this state. This square goes to 1. So you don't have any memory of the initial states. So that part is resolved. So the answer to this is it becomes an O bar. But physical mechanics. Oh. Oh. I'm sorry. Hello? Yeah. So, what happens is that if your trace out here, if you do this quantity depends on the average energy of the system. Okay? Or in other words, instead of a microcanonical, if you used a canonical ensemble, this would depend on the temperature. By equivalence of ensemble, average energy and temperature can be related. So that's. However, random matrix theory is just going to give you one answer, no matter what the energy details are. Okay? So that part is inconsistent. And therefore, you need a little bit something more, in some sense, to sort of patch between these two predictions. Okay? And here, there is this really, seminal work by Srednicki and then Deutsch, and also Marcus Riegel did some really interesting early work. And so they came up with a hypothesis. Okay? This is, as far to the best of my knowledge, this is not a proved thing, but this is a guess which works for most of the times.
You said RMT only gives particle.
If you remember the RMT results, this OMM, the diagonal component, is just a O bar, which is a constant. Okay, that doesn't depend on the details of the system, and therefore it's okay. So let me try to write here. Okay, so the eigenstate thermalization hypothesis is a statement about the nature of this matrix element, and it tells you that between any two states M and N, eigenstates M and N, this quantity is just OE delta Mn. I'm going to define what E is, plus so let me carefully explain all of this, okay? So E essentially is just the average energy of the two levels, okay? Therefore, in that sense, it depends on the levels, okay? Omega is their energy difference, okay? And this is the entropy of the system. This Rmn is a pseudo-random number with mean 0 and variance 1, just as we put a random number for this. Now, the fact that it's not exactly random and it has some correlations in it is not going to show up in whatever I'm going to discuss here. It only shows up when you talk about out-of-time correlators, but not the standard things that I'm going to talk about. So I'm going to take them as random numbers, okay, with mean 0 and variance 1. Okay. Gaussian random numbers with mean 0 and variance 1. Okay. Now, the difference with RMT is that now this is a energy dependent stuff. Okay. So, okay. And you could ask that why am I putting a entropy all of a sudden out here? This exponential of minus entropy is really 1 over the number of microstates in any given macrostate that you can think of this system. You know, that's 1 over d. And that's just this, oh sorry, there is a factor of 2 here. So this 1 over square root of d that appeared in the random matrix theory is essentially represented in this manner. It just tells you that M and N, if it is one of those two typical microstates, there are and you start from a state M, there are lots of these N's that you can go into, and individual matrix elements are suppressed by the total number of such states, which is 1 over d, 1 over square root of d, and therefore this is exponential s by 2. Okay. But given this, let us see what the consequences are. Okay. So as I said, you know, these are basically, this is still a hypothesis, and there is, I don't know of any proof that this is exactly the case. We know systems where this do not work, and I'm going to come to that towards the later part of this in the next lecture. But overall, this gives a remarkably strong way of understanding, you know, how this dynamics of an ergodic quantum system behaves. Okay.
So the factor of F I need because the left-hand side is a function of the gap and the average, and the F factor.
Yeah.
On the right-hand side, I need because the left-hand side is a function of
gap and the average. So what you are doing here, remember that in this case for the random matrix, this Rmn was there. What you had here was expectation of O square, I guess, something like that. That again was a thing which didn't depend on any energy. But O square, you know, depends typically on 2 energy scales. And that's why you put it like this. Okay. And this F E omega, which we are going to study in detail, that is a smooth function of both of its arguments. Okay. It's a slowly varying smooth function of both of its arguments. And we are going to see how, just one second, we are going to see how this varies at different energy scales. Yeah.
I had one question related to this RMN. So this ETH, it's not a random matrix theory, right? For a particular Hamilton.
No, the difference is that now we have put in some energy dependencies in the prefactors of different things.
I see. So this RMN is coming because
RMN is, see, you take your Q from the random matrix theory because it got something right, that your exponentially suppressed off-diagonal matrix elements and your memory non-retainment of the diagonal matrix element, but you need to improve it a little bit. So what you do is you keep this structure to be the same, but now you put in energy dependence everywhere in ways you can. Okay, so that's the intuition behind the hypothesis actually.
And the smooth function, that aspect comes about because we are considering the mid spectrum.
Yeah, it's all in this mid spectrum where there are thermal states. If you go away from that, there is no.
So is there any particular structure of that function?
Yeah, well, I'm going to come to the behavior of that function. It's very important when it comes to how do you call it? So when you come to studying this dynamics, correlation functions and fluctuations and stuff like that, it's very important. We are going to come to that. Yeah.
Is there any reason why you add this entropy term with the random number in this hypothesis?
No, this is my hypothesis, you see. So I'm just saying that this is the case. So the logic behind this is that this is like 1 over square root of d, d being the number of states in your Hilbert space within that energy band. And so in the random matrix theory, I had a suppression factor like that. I just want to mimic it. But I want to mimic it in a way, because entropy is after all log d, right? I mean, so I can mimic it in this way. And that's it. Okay. So the first thing, yeah.
In this way of doing this f of e omega, roughly speaking, this RMT result is just square root of trace of O square.
Which is independent of E and omega.
Independent of energy. So it's just to put in some energy dependence.
Yeah, because that's what the StatMech answer is telling you to do, right?
And for a typical initial state, I will be roughly energy independent.
No. Why?
If I hit the O operator or typical initial state.
No, this is my matrix element between two eigenstates. What do you mean typical? There is no information about any initial state in any of this. This is just the structure of the matrix element. The initial state information is out here in the CMs. Okay, this is not a hypothesis about CMs. This is a hypothesis about OMs. There is no initial signal. Okay.
That D in the RMT
Yeah.
that is directly connected to e to the power minus.
Yeah. Log D. S is log D, roughly speaking. So square root of 1 over D is like exponential minus S by 2. I mean, this is a rough analogy, but I mean, yeah. So that's the way to sort of.
And trace O square, I think you have repeatedly answered.
No.
That trace O square is if somehow you are.
Trace rho square? What?
O square, trace O square from the.
Oh, I'm going to compute this trace O square even here, and we are going to see that it depends on this F and other things. Okay. That is what I intend to do next. So let me proceed, and then we can sort of. So the first thing is that suppose I just consider the expectation of O now. Okay, what does this do? So the expectation of O, I can now forget about the off-diagonal term because it's exponentially suppressed. Okay, so that's the thing. So now my expectation of O in the to the steady state answer for this now becomes summation over m mod Cm square, and then O of E. Of course, delta m in square is not this thing, and this is typically written as this. Rho d, d is the diagonal ensemble. So if you compute the density matrix of a given system and only retain the diagonal terms, that would be just your mod Cm square, and then that's the expectation of this. Okay. Now the question is, this is just another way of writing this. But it's still not equal to the microcanonical ensemble because this is a different density matrix that I have considered. It's not the microcanonical. But here, the sub-extensivity of energy fluctuation comes in, and that's why we can show, and as I'm going to show, that these two results are identical to the leading order. Okay. Why? Because you see, this quantity has a O of E, right? But now, let me just expand this O of E as O of E bar, which is the average energy of the system, plus of course E minus E bar, O prime of E bar, plus half E minus E bar square, O double prime of E bar, and so on. Okay. So I'm going to take this and expand. Okay. Put this back. So the first term is O of E bar, because trace rho is just 1 and this doesn't have a E dependence anymore. Okay. The second term is 0 because it has a E minus E bar. So trace of rho times E minus E bar is just 0 because trace of rho E is what gives you E bar. Okay. The third term would give you some fluctuations, which I'm going to call as delta E dE square, whatever that fluctuation is fluctuation of energy times O double prime E bar as a second derivative. Okay. Now, if I do the same thing, okay, maybe I can, sorry? Oh, I see, sorry. Okay, so the point is that now, let me do exactly the same thing with microcanonical ensemble. So if I do this, so let me call this delta O dE out here, and then let me take delta O ME, which is this microcanonical result. So you see, instead of dE, if I put a trace of rho ME out here times O of E, I can again do this expansion. The first term again is just O of E bar. It's completely independent of what distribution you take. Yeah, you had a question.
That E bar, that's the average energy?
That's the average initial energy of the system. Psi naught H psi naught. Yeah, that's the initial. So you start from an initial state. That has an average. That has an expectation value. That's your average energy. In other words, you can also, if you are using a canonical ensemble, call it the temperature of the system. Okay. You can just say that this energy is some e to the power minus beta H expectation and then feed the parameter beta to get a temperature. This is the average energy. Okay. And the point is that any deviation from this average energy in any ergodic system is sub-extensive. The energy fluctuations are sub-extensive, right? So that's the. So this is OE bar, and then there is a half delta E square ME, and this will of course be different. This depends on how the fluctuations are, divided by O del. So the difference between these two only comes because of this, and therefore I can write ODE is equal to OME, expectation of OME plus half delta E dE square minus delta E AB square O double prime and then other terms. Okay? Yeah.
So basically we have made a assumption regarding sub-extensivity of the deviation from the E bar. The fact that we can do that.
So I am only talking about systems where the energy fluctuations are sub-extensive. So if these are sub-extensive and it goes to 0, then you see that the quantum mechanical answer, which is this diagonal ensemble thing, after putting in this ETH, becomes equal to the microcanonical answer, to the 0th order. Yeah. Huh? Diagonal ensemble. D is diagonal ensemble. So you create your density matrix and then you forget about the off-diagonal elements. It's just this diagonal.
So does this then exclude the long-range interacting systems?
Once the equivalence of ensemble is gone, I don't really know how it. I have never studied ETH in the context of long-range systems. So.
This extensivity argument. That
Yeah, that's not going to work. So then there is no reason to expect that this kind of general statements are going to hold. Yeah. So at least the way typically people talk about this ETH showing general results, this agreement with the microcanonical and that being equivalent to some canonical, all of these results as this crucial component of sub-extensive energy fluctuation. If that's gone, then I think this is gone. I at least don't see a way why it should hold.
Also, like, what is the justification for, what is the need of using diagonal ensemble?
No, diagonal ensemble is a quantum mechanical result, right?
It's just an analog.
Yeah, no, not the analog. The quantum mechanical result is going to tell you, provided you have put in the ETH thing, it's just going to tell you that it's trace rho d. So you compute your density matrix, okay? So what will happen is that in that density matrix, the diagonal elements are just these mod CM squares, right?
Yes.
And therefore, if you forget about the off-diagonal part of that density matrix, then this is essentially taking trace of your operator with respect to this.
No, I was just thinking, like, but that is another, like, I mean, we are at the end calculating. Okay, I got it.
So that is the quantum mechanical answer out here. And because of this sub-extensive nature, that's to leading order is equivalent to the stat mech answer.
That is the definition of the diagonal answer.
That is the definition of pattern. Yeah. Okay. So the next thing is that, so suppose now I want to, I'm not, okay, I have half an hour. Okay, good. So let me see. Just give me 1 second. So I have done this, that. What do I want? Okay. So now comes this thing that you could ask that suppose, I have reached this steady state. I would still have some fluctuations over this steady state value for any finite size system. How do these fluctuations behave? What is the prediction of this? So to do this, what we want to do is to compute the following quantity, which is how strong, so just to see how strongly the system fluctuates about its steady state value. So I can calculate the following. I can calculate a measure of this variance, sigma O square, which is 1 over t. Okay, so limit t tending to infinity. Why is this chalk not writing properly? 0 to t dt OT mod square minus over square. Okay. So I'll just take, so what am I doing? I'm taking some OT operator, squaring it, and then averaging over a time window, okay, from some 0 to t, and then taking the expectation of that. So it's a temporal average over some time frame, and I want to see that how that temporal average is different from what the steady state value predicts. Okay.
OT is the expectation of something?
OT is just this. Okay. So now if I write this down, this is limit t tending to infinity, 1 over t dt t to 0 to t, and then I'm going to sum over all these energy eigenstates mn pq. I'm not putting in the ETH answers as yet. I'm just simply writing this down from a quantum mechanics perspective. So I'm going to have e to the power I epsilon m is epsilon n plus epsilon p minus epsilon q t over h bar, and then OMN star and OPQ. And then this entire thing will have a minus O bar square that's coming from here. Okay? It's just writing this, this matrix elements in longhand. Something that comes in from here. Just substituting this expression for O of t out there. Now you see that there is of course one term which is m equal to n and p equal to q, and that term is exactly going to cancel this O bar square. Okay? But then there is another term where m is equal to q and n is equal to p, which is going to be there, And if you do this, averaging, so what you are going to get is summation over pq. You can trade off m and n, mod cp square mod cq square, and then opq mod square. Okay?
In the above expression, there should be CP, CQ, CN.
Yeah, sorry. Cm star, Cn, Cp star, Cq. Thank you. Sorry about that. Yeah. Okay. So this, where P is not equal to Q, because if P is equal to Q, it goes right in there. Okay. So this means that this quantity is of the order exponential of minus S of E because of the off-diagonal matrix elements. Okay. And therefore, fluctuations over my steady state is exponentially suppressed to 1 again. So, and larger the system size, better this suppression is. So that's also a ETH prediction, that the steady state would be stable, and for large enough system size, the fluctuations will be minuscule. Remember that this doesn't mean that the fluctuations that we observe in the laboratory, in the initial times, that is suppressed exponentially. That's not what it means, okay? Once you have reached the steady state and you have gone up to some amount of time there, how much variation over that steady state do you have? That's what this means, okay? So this is one thing that I wanted to say. Yeah.
How do we write
This one? Or that one? This one? Oh, because, see, the point is that if you have m equal to n and p equal to q, these are the diagonal elements, and that's going to just do this. But there is also another way to satisfy this. Okay, the integral is going to go to 0 unless this exponent is 0, right? So another way of satisfying this is m equal to q and n equal to p. So you put that in, then put those m, n's out here, and you are going to find this.
Yeah, that is okay. I'm just asking, why do you write e to the power minus 1?
Oh, why am I right? Because you see, these are off-diagonal matrix elements. Remember, P and Q cannot be the same. And therefore, by ETH answers, the off-diagonal matrix element, remember, there was an exponential minus s by 2 factor. So this will be very complicated, but it will at least be proportional to exponential minus of the entropy.
So in the last minus over square is
Because of this.
the last sum over p.
No. No, this is not. So here there is a minus over square, but there is a term where m is equal to n and p equal to q. That term is going to cancel this. In addition, there is a term which is this, where p is not equal to q. Okay?
So in this last line, it is explicit that p is not equal to q.
Yeah. You can see this actually. Okay. Is everybody okay with this, or do I need more explanation? Or? Okay. Now the next thing, so before I go into more serious this thing about the off-diagonal matrix element, one thing that I need to say is that why and when this ETH results, why and when this ETH results, if they at all coincide with that of random matrix theory, what's the connection? And the connection is that if you want to just look at your system within a very narrow energy window over which your density of state remains the constant, Then in a typical system, that energy window will have roughly the average energy. And then O of E bar is just going to tell you that that's basically the expectation value of O. Okay? So O of E bar within that energy window is going to go to a constant. Some O bar. Okay? Because it's a very narrow energy window, it doesn't change much within this. And therefore, sorry, O of E, not E bar. I mean, the energy of this states within that energy. And then in that limit, ETH and RMT, random matrix theory, is going to coincide because the energy dependencies go away if you take a. So what is this energy scale? So if you have a dissipative quantum system, it turns out that this scale is a scale called the Thouless energy, ET, which goes as HD over L square, and D is the, okay, I should say D not, D is the dissipation constant, is a typical this thing. So in a dissipative single particle system, this is typically the time taken by an electron to move across the system during its dissipative dynamics and the energy scale that comes from this. But here it turns out that if you take a energy of this width, and this D has to be, sort of is a parameter that you need to decide, then this is the energy scale below which these two results essentially coincide. Okay? But this is just for dissipative systems. So for example, why this kind of things never work for glassy systems, for example. In glassy system, this energy scale is typically some epsilon by tau star, where tau star is the longest time scale in the glassy problem. And therefore, this energy scale goes to 0 because, glass, as we know, has a tremendously long time scale. So in that case, whether ETH works or not is a different question, but it will never going to coincide with the random matrix theory. Okay? And in general, ETH doesn't work because it's not an ergodic system in that sense. Okay? So glasses are tricky. Okay? So but the point is that, forget about these energy scales and stuff like that. The point is that if you are in the middle of the spectrum, you take a small enough energy window over which these matrix elements, do not vary much. You can replace them by an energy independent answer, and then it's like random matrix theory. So the other way of understanding this is that if you are thinking not in terms of microcanonical ensemble, but in terms of canonical ensemble, RMT is sort of the infinite temperature value. Because if you put beta equal to 0, then all the energy dependencies in your system goes away. Because every state is equally probable. When you draw a typical state, any state is as good as another. And that's where you coincide with the random matrix, this thing. Okay? So typically in driven systems, this is one thing that can happen, that you go to this infinite temperature steady state, and there are certain predictions of RMT do work in certain sense. Okay? But overall, just take a small enough energy window, and then these two are the same. Yeah.
So is there any physical reason why this Thouless scale would go as 1 by L square?
Okay, I don't have this or that. So for a, okay, let me see. So in diffusive dynamics, your typical time scale of an electron to go from one end of a conductor by other, this goes as d by L square by d, that is. Okay, so and then the energy scale is just constructed out of that. It's really in that time that L square dependence comes in. How it exactly comes in, I don't have it at the top of my head.
But
Sorry.
then what is exactly the thing what is diffusing in the system?
No, here there is no analog of that because you don't have a quasi-particle description of anything. Here, this result that it catches this. So what do people do? You take this system, you numerically check, when the random matrix and this thing, and then you find a scale. But then you do finite size analysis, and you will see that this scale goes as 1 over L square. And then people took cue from the fact that for single particle diffusive systems, there is this Thouless scale which goes as 1 over L square, and they patched this too. Okay. There are more intuitions into this. I haven't gone into the details of this so much. Okay. But the review article that I suggested had some more discussions. You can take a look if you want. Any other questions? What is what? Sorry? D0.
Yeah,
Oh, this one. This one is the typical dissipative constant that comes in a dissipative system. So what happens is that if you have a single particle system and the electron undergoes a diffusive dynamics, there is this diffusion constant divided by L square, which gives you a typical time scale, the system size, going from one end of the system to the other. Okay, and the energy is constructed out of that.
So is it for the beta electricity zero limit, or is it also true for beta finite?
No, again, I mean, the point is that if it is finite beta, so if you are basically, so it will deviate a bit, but I mean, it's then a matter of numerics. I mean, how much, strictly speaking, only beta equal to 0. Okay, so I'm going to now talk about the off-diagonal part of the matrix elements and its properties. Okay, at least start that discussion and then we'll carry over in the next. Okay, so as we know, for the expectation value of a typical operator, the off-diagonal matrix elements don't show up because it's exponentially suppressed. But when you are looking at fluctuations or connected correlators, so to speak, then of course this thing shows up. Okay, so what we need to calculate is let me just do this properly. So I want to calculate the connected correlator of O. Let me call it as delta On. It's matrix element of this connected correlator between a given eigenstate n. So that definition is n O square n minus n O n. Okay? Or let me just write square. Forget about this complex configuration. Okay. This by definition is n not equal to m, sum over m not equal to n okay, mod square that is. The reason is that what I'm doing, I'm breaking this into O and O and then inserting a complete set of states. The set where m is equal to n gets cancelled here. That's the disconnected part of the correlator, and then the rest is this. Okay. So this, if I write down, this is typically the matrix element of ETH where n is not equal to m. So this would be summation over m and then exponential minus s of e, where, okay, mod f e omega square okay. I'm just taking this matrix element, substituting it here and then taking its mod square. Okay.
This E is the energy of n.
N, yeah. So E is En plus Em2 and omega is En minus Em. Okay? So let me just explicitly write this so that there is no problem later. And okay. Okay. That's the. Now let me redefine variables so that I'll call En to be E and Em to be E plus omega by 2. This is just a restatement of that. Okay. And I want to write this in terms of E. Sorry. Yeah, okay. I don't really care. This both has E. So then my delta when here is exponential of m okay. I'm just writing changing variables. Now what I'm going to appeal is that this sum over m, when you have a term like this, given that f is a smooth function and this quantity is also a smooth function, this Rmn square, the sum will just average it over to 1 because it's just the variance of this random number. Okay. So I'm going to replace this by expectation of Rmn square, which is equal to 1. Okay. That's the first step. The second step is that instead of carrying out a sum, I'm going to convert it into an integral over E. Okay. And if I do that, then this will be some dE and then some density of state, let me call it as omega E, exponential minus s E plus omega by 2 mod f square. I'm not going to write the, okay, let me write anyway, sorry. E plus omega by 2 and omega mod square. Yeah.
Omega should be defined En minus En, right? That's when it gives En equals to E plus omega.
Yeah, probably. Sorry, yeah, okay. Okay, so the point is that when I have this, I need to find out what this is. Okay, and this, if I take an energy window of D, a small energy window, then this is just the number of states in that energy window, right? That's the density of state. And this I know is going to go as exponential of S because that number is D basically, right? So then I can write this as dE exponential of S of E plus omega minus S of E plus omega by 2, okay, and then this quantity, okay. Because this was a sum over m and m was E plus omega and therefore this will have this exponent E plus omega. This energy dependence as E plus omega. So okay, is everything clear till now or is there a, yeah. So what I'm doing is that so the first thing I did is that this Rmn square, so that's a random number, okay, and the other two terms which multiplies this random number are reasonably smooth functions. So my statement is that when I do this sum, I can replace this random Rmn square by its expectation. And Rmn square expectation is just the variance, which is 1. Okay, so I'll replace that. The next step is that sum over m is something that I am going to convert into an energy integral. Because I am summing over energy eigenstate, and then the only thing I need is the density of state, right? To convert that sum. This omega E is the density of state, but that's just the number of states in an energy bunch, and that will go as 1 over d. Okay? And therefore, that's exponential s of E plus omega. And because I was summing over m, Em was E plus omega, and then, you know. I'm sorry?
Omega E, you are writing as e power s e plus omega
Yeah.
minus.
No. Omega is a density of states. There is a large number of it. It has to be exponential. See, this had a minus, not the other one. Okay. So now I am going to expand. So because these are smooth functions of E, okay, I am going to expand this in omega. So to expand this, you see, I have a relation that del S del E is just beta, right? Which is inverse of temperature. That's the definition of temperature in a system. So this I can write as d E. Then the first term is exponential beta omega by 2. Okay, I'm expanding in omega. And here I'm going to expand only in the first this thing. So this will come as mod f E omega square plus omega by 2 f E this means that is the first derivative. This means that this is the first derivative of del f with respect to E, the mod f square with respect to E. Okay, just expanding this thing in the first. So this is the result. So the correlation essentially depends on E omega as well as its derivative. But if E omega is a reasonably smooth function, then one can say that this just depends on the mod f square, okay, with some factors of beta omega by 2, and it has to be integrated over. So in the so we will sort of look in yeah.
So this derivative is with respect to omega.
E.
One small note.
Sorry?
This omega E you write it is equal S E plus omega. Why did you put the omega?
Because it comes from EM. The sum is over M. Because the definition of that is, So En was E. EM has to be E plus omega. Otherwise the gap is not going to be omega. Okay. So this is my delta On. Okay. And this is the result relating equal time, so the connected equal time correlation functions with mod f square. Okay. So in the next class, I'm not going to start now because I'll do this in the next class. What I'm going to do is to sort of now look into the unequal time correlator and get some fluctuation dissipation relation relating f with this, and then we'll see why there is a typical statement that people make that thermalization occurs eigenstate by eigenstate. I never understood this statement before, but I think I understand what they mean now, and I'm going to sort of show why this is the case. Okay. So apparently it turns out that every correlator in a given expectation of any operator, of a typical operator in any given energy state, that itself has a fluctuation dissipation theorem for any eigenstate within that band, mid spectrum band. And that's why it's a bit different from a generic fluctuation dissipation of the entire system, a more powerful thing. And before ending this, there is one thing that I must say, which I probably forgot to tell you, that I of course wrote down structure for a operator, matrix element of operators between two eigenstates. And then you can ask me that whether this holds for every operator. The answer is no. Then you can ask me that which operator does it hold for, and the answer is I don't know. The point is that there is no rigorous mathematical understanding as to which operators would satisfy ETH and which do not. But typically what happens is that if you have local enough operators, they do satisfy ETH, and I think there was some study in some specific system which shows that if you have a system size of length L, and if you have an operator length, the initial operator having support over L eigenstates, so as long as small l is of the order L by 2 or lower, there is some resemblance with ETH, but of course the results, the fluctuations in the results increase as you increase this operator length. What it doesn't hold for are things like projection operators. So if you have a projection operator whose matrix element is very well localized in some particular specific energy, then there is no ETH there. And that's easy to see because you see, suppose I take a projection operator which projects me to the ground state. And clearly that ground state is not thermal and you don't expect ETH there. Okay, so one needs to be a bit careful, but this is very useful in understanding local correlations of standard operators that we typically study in many-body systems. So I think I'm going to stop here now, and in the next class I'm going to continue with that and then talk about violations and stuff like that.
Are there any questions? Oh,
yeah.
These M's, we are summing over all the M's or like some M?
Except the M.
Except M.
Yeah, well, of course, we are going to be in that band where, the thermal states are there and ETH has to hold and stuff like that. But in any case, it doesn't matter because you see, if N is in the band, and if this, so we'll see that this F omega has the property that it again decays for large cap. Okay, so it really doesn't matter if you go outside. That F would be very small.
Was that dependent on
yeah. So we're going to come to that in the next scene.
Anyone else?
So last time you said that this F prime, the first derivative, we can neglect phi?
It's a smooth function. So its derivative is going to be small. Locally, the derivative is almost always small.
Okay, if not, let's thank Krishnendu.